There is a question that almost no one asks in the right direction. People ask how old the universe is, and the answer is 13.8 billion years, and that number feels large enough that the conversation usually stops there, as if 13.8 billion years is so enormous that asking what comes next is somehow beside the point. But the universe is not done. It has not reached anything like a midpoint or a conclusion or a stable resting state. It is 13.8 billion years into a process that will continue for durations so incomprehensibly longer than its current age that 13.8 billion years is, by comparison, the first breath of a life that will last for trillions of lifetimes. The universe has an expiration date, not for a long time by any measure we can apply to human experience. But the date exists, it is written into the physics, and what comes after it is not nothing. It is something stranger than nothing, and stranger than anything the universe currently contains. Tonight we are going to follow the universe from right now to the end, and then past the end, and find out what the physics says is waiting on the other side of everything we have ever called existence. Welcome to Dusk and Discovery. Settle in. This one goes all the way to the end. If you want more nights like this, subscribe. Now, let us go forward. The first thing to establish is what kind of ending we are talking about, because the word ending applied to the universe can mean several different things depending on which physical scenario you are considering. The universe does not end in the sense of ceasing to exist in a moment of destruction, at least not according to the physics we currently understand. It ends in a more subtle and in some ways more disquieting sense. It runs down. It exhausts its usable gradients. It reaches a state in which nothing of interest can happen anymore, not because the laws of physics have changed, but because the conditions required for interesting things to happen have been consumed by the long running of those laws. The death of the universe is not a bang. It is a slow and irreversible settling into the most uniform, most featureless, most energetically inert state that matter and energy are capable of reaching. To understand why this ending is inevitable, you need to understand what the second law of thermodynamics actually says, and why it applies to the universe as a whole. The second law says that in any closed system, entropy, the measure of the number of possible microscopic arrangements consistent with the macroscopic state of the system, tends to increase or at best remain constant over time. A closed system that starts in a low entropy state, a state with few possible microscopic arrangements, will naturally evolve toward higher entropy states with more possible arrangements, because there are simply more ways to be disordered than ordered, and random processes therefore drive systems toward disorder over time. A hot object in contact with a cold one transfers heat from hot to cold, not the reverse, because the final state where both objects are at the same temperature has vastly more microscopic arrangements than the initial state where one is hot and one is cold. The universe, as best we can determine, is a closed system in the relevant sense. There is no outside reservoir from which it draws low-entropy energy, and no outside sink into which it dumps high-entropy waste. The entropy of the universe can only increase, and the universe began, as we discussed in previous nights, in an extraordinarily low-entropy state, a hot, dense, nearly uniform distribution of matter and energy that has been evolving toward higher entropy ever since the Big Bang. Every process that has occurred in the universe, every star that has burned, every chemical reaction that has proceeded, every gravitational collapse that has formed a structure, every explosion that has scattered material across space, has increased the total entropy of the universe. The direction of entropy increase is the direction of time itself. The reason that time has an arrow pointing from past to future rather than being symmetric. The reason you remember yesterday but not tomorrow. The endpoint of this process is what physicists call heat death, the state of maximum entropy, the state in which the universe has exhausted all its usable gradients and reached a condition of thermal equilibrium where every region of space is at the same temperature and no spontaneous process can occur because there is no free energy left to drive one. Heat death is not hot. The name is misleading. Heat death is the state of maximum coldness, the state closest to absolute zero that the physics of an expanding universe permits, a state in which every concentration of energy has dispersed, every star has burned out, every black hole has evaporated, and the remaining radiation and matter are spread as uniformly as possible through a space that is still expanding and still cooling. It is the most perfect quiet that the laws of physics can produce. The path from where we are now to that quiet is a journey through several distinct eras of cosmic history, each one dominated by different kinds of objects and different physical processes, each one lasting for durations that dwarf the previous one. We have touched on these eras in previous videos, but tonight we are going to walk through them in full from the current moment to the end, and then we are going to ask the question that the story of heat death almost always stops too soon to answer. What happens in the infinite time after heat death? What does physics say about the universe in the state of maximum entropy, sustained forever by the expansion of space? The answer is not nothing, and it is not comfortable. The era we currently inhabit is called the Stelliferous Era, the era of stars. It began roughly 100 million years after the Big Bang, when the universe had cooled enough for the first molecular clouds to collapse and ignite the first stellar nuclear reactions. It will end roughly 100 trillion years from now, when the last molecular cloud has produced the last generation of stars, and the stellar fuel supply of the galaxy has been exhausted. 100 trillion years is 10 to the power of 14 years. The current age of the universe is approximately 10 to the power of 10 years. We are in the early part of the Stelliferous Era. Not the beginning, the first stars formed 10 billion years before us, but well short of the midpoint, and nowhere near the end. During the Stelliferous Era, the universe is dominated by the electromagnetic radiation of burning stars, the gravitational structures of galaxies and clusters, and the ongoing processes of star formation and stellar death that we spent the previous video examining in detail. The sky is full of light. Chemical enrichment of the interstellar medium is ongoing. New stars and planetary systems form from the enriched gas. Life, wherever it exists, has access to the steady energy flux of nearby stars. The universe is busy, in the sense that events are happening at a rate that would be recognizable as activity to any observer embedded in it. The end of the Stelliferous Era is not a dramatic event. It is a gradual fade-out. The star formation rate, which has already been declining for several billion years from its peak approximately 10 billion years ago, continues to decline as the supply of cool gas available for star formation is consumed. The last stars to form will be red dwarfs, the smallest and most fuel-efficient stars, which can burn for trillions of years on their modest hydrogen reserves. The very last red dwarfs will still be burning when the universe is 1,000 times its current age, but they are consuming their fuel, and eventually even they will exhaust it and cool toward the endpoint of all stars with insufficient mass for a supernova, the white dwarf. As the last stars fade and the last stellar remnants cool, the universe transitions into the degenerate era. This is the era dominated by the compact remnants of stellar death, white dwarfs, neutron stars, and black holes. The sky in this era is dark in any wavelength that a human eye could perceive. There are no burning stars. There is no nebulosity lit by young clusters. There is no diffuse glow of an active galaxy. There is only the faint and fatting thermal radiation of cooling white dwarfs, the radio pulses of slowly spinning down pulsars, the gravitational influence of invisible black holes, and the pervasive microwave background of the Big Bang, stretched to even longer wavelengths by the billions of additional years of cosmic expansion. The universe is not silent in the technical sense, because thermal radiation still propagates, but it is dark and it is cooling. And the rate at which interesting things happen has slowed dramatically from anything in the Stelliferous Era. The degenerate era is long. Depending on whether proton decay occurs and on what timescale, it lasts from roughly 10 to the power of 36 years if proton decay proceeds at the theoretically predicted rate, to longer if protons are stable. The question of proton stability is one of the important open questions in particle physics. The standard model of particle physics, the best theory of fundamental particles and forces we have, predicts that protons are absolutely stable. But many extensions of the standard model, including grand unified theories that attempt to unify the strong, weak, and electromagnetic forces into a single theoretical framework, predict that protons decay on a timescale of roughly 10 to the power of 34 to 36 years. If proton decay occurs, the white dwarfs and neutron stars of the degenerate era will gradually dissolve over this timescale as their constituent protons decay into lighter particles and radiation, leaving behind only the black holes and a dilute bath of radiation. If protons are stable, the white dwarfs cool indefinitely toward the true ground state of ordinary matter. Whether proton decay occurs or not changes the details of the degenerate era, but not its ultimate endpoint. Even stable protons in white dwarfs do not produce stability against all processes forever. Over timescales vastly longer than the proton decay timescale, even if protons are perfectly stable, the crystalline structure of a cold white dwarf will undergo quantum tunneling rearrangements, and the white dwarf will slowly, imperceptibly, convert itself from a mixed composition of carbon and oxygen into pure iron, the most stable nuclear configuration, releasing a tiny amount of energy in the process. This iron conversion takes roughly 10 to the power of 1,500 years, a number so large that writing it out in full would require more digits than there are atoms in the observable universe. But it is not infinite, and the physics permits it, so over a truly infinite time it occurs. Even the most stable form of ordinary matter at low temperature is not perfectly static on infinite timescales. Everything changes, given enough time, even if the timescale required makes the current age of the universe look like a rounding error. Eventually, the black holes dominate. The black holes formed from the most massive stellar deaths, the ones that have been present since the early universe, have been slowly accreting whatever material drifts within their gravitational reach, and occasionally merging with each other as binary systems spiral together through gravitational wave emission. They are not growing rapidly in the sparse environment of the degenerate era, but they are growing, and by the time the last white dwarfs have either decayed through proton decay or converted to iron through quantum tunneling, the universe is dominated by a population of black holes ranging in mass from a few solar masses to billions of solar masses, the supermassive black holes at the centers of the remnant galaxy clusters that gravity has held together through all the preceding eras. This is the black hole era. It is the era in which the most massive and long-lived objects produced by the universe's entire history of stellar birth and death are the last complex structures remaining. They do not interact with each other significantly. They do not radiate in any way detectable by conventional electromagnetic telescopes. They simply exist, drifting through a universe that has otherwise gone dark, their gravitational fields curving the spacetime around them as they have since they formed, their event horizons absorbing the occasional particle that drifts close enough, their Hawking radiation trickling outward at temperatures far below the cosmic microwave background temperature of the era. The Hawking temperature of a black hole is inversely proportional to its mass. A stellar mass black hole has a Hawking temperature of billionths of a degree above absolute zero. A supermassive black hole of a billion solar masses has a Hawking temperature roughly a billion times smaller than that, a number so close to absolute zero that it is effectively indistinguishable from zero by any physical measurement. But it is not zero. And in the black hole era, when the temperature of the surrounding universe has dropped far below even the Hawking temperature of stellar mass black holes, the direction of heat flow reverses. The cosmic microwave background, cooled by the additional expansion of the universe over the preceding eras, eventually drops below the Hawking temperature of the black holes, and at that point, the black holes begin to lose mass through Hawking radiation faster than they gain it through accretion. the evaporation begins. For stellar mass black holes, the evaporation timescale is roughly 10 to the power of 67 years. For a supermassive black hole of 10 billion solar masses, the evaporation timescale is approximately 10 to the power of 100 years. These numbers are staggering in the specific sense that they are staggering relative to the already staggering numbers that describe the earlier eras. The entire stelliferous era, 100 trillion years, is 10 to the power of 14 years. The evaporation time of a supermassive black hole is 10 to the power of 100 years. The ratio between them is 10 to the power of 86. The black hole era, measured from the end of the stelliferous era to the evaporation of the last supermassive black hole, is longer than the stelliferous era by a factor comparable to the number of atoms in the observable universe. The era of stars, which contains all of stellar evolution and chemical enrichment, and every living world and everything we have ever called cosmic history, is an eye blink at the beginning of the black hole era. The evaporation of a black hole through Hawking radiation is not steady throughout the process. For most of the evaporation time, the Hawking radiation is so cold and so faint as to be essentially undetectable by any instrument we could conceive. The temperature rises slowly as the mass decreases, because the Hawking temperature is inversely proportional to the mass, and as the mass decreases, the temperature increases. In the final seconds of evaporation, as the black hole mass drops to a tiny fraction of its original value and the temperature rises to extreme levels, the evaporation rate accelerates dramatically, culminating in a final burst of Hawking radiation that releases the remaining mass energy of the black hole in a brief flash. For a stellar mass black hole, this final burst has a luminosity comparable to a modest nuclear weapon. For a supermassive black hole, the final burst is more energetic, briefly rivaling or exceeding the luminosity of the entire stelliferous era galaxy before the silence resumes. After the last supermassive black hole has evaporated, the universe enters what cosmologists call the dark era, the state of maximum entropy, the heat death. There are no stars. There are no stellar remnants. There are no black holes. There is only the radiation, a dilute and uniform bath of photons and neutrinos at a temperature indistinguishably close to absolute zero, expanding forever through an infinite space. The cosmic microwave background, still present but now so cold and so stretched that its photons have wavelengths larger than the observable universe, forms the background against which nothing else happens. The relic neutrinos from the Big Bang are still there, streaming through a universe that has nothing left to interact with them. The gravitational wave background is still propagating, its amplitude diluted by the expansion to below any level that could drive a physical process. The quantum field ground state, the vacuum energy, is still present, still driving the accelerating expansion of space, still representing the cosmological constant that will push space apart forever. This is the expiration date. The moment when the last black hole evaporates and the universe achieves maximum entropy is the end of the universe in the sense that it is the end of the universe as a place where things happen, not the end of the universe in the sense of a boundary or a cessation of existence. The space continues. The laws of physics continue. The quantum fields continue to fluctuate in their ground state. The expansion continues. But there is nothing left that the physics can do anything interesting with. The gradients are gone. The free energy is exhausted. The structures have dissolved. The universe has run its program to completion, and what remains is the output, a cold, dark uniform, expanding nothing that nevertheless is not quite nothing. Because the quantum vacuum is still there, and the expansion is still happening, and the physics is still running. And then the physics does something. This is where most discussions of the fate of the universe stop, because heat death sounds like the end, and the mind does not naturally ask what comes after the end. But the laws of physics do not stop operating at heat death. They continue operating in a universe that has reached maximum entropy, and the laws of physics operating in a state of maximum entropy have consequences that are strange and disturbing and important for understanding what the universe actually is over truly infinite timescales. The first consequence is quantum fluctuations. The quantum vacuum, as we discussed in the empty space video, is not static. It fluctuates. The uncertainty principle prevents the quantum fields from settling to exactly zero at any point in space, and these fluctuations are as vigorous in the heat-death universe as they were in the early universe, because the quantum ground state does not depend on the temperature or the entropy of the surrounding matter. In the heat-death universe, the fluctuations are all that is left, and in an infinite universe over an infinite time, the fluctuations will occasionally, spontaneously produce something. The probability of a given quantum fluctuation is exponentially suppressed by its size and complexity. A fluctuation that produces a single particle from the vacuum is much more probable than a fluctuation that produces two particles, which is much more probable than a fluctuation that produces a stable atom, which is vastly more probable than a fluctuation that produces a molecule, which is incomprehensibly more probable than a fluctuation that produces a cell, which is incomprehensibly more probable than a fluctuation that produces a brain. But in a universe of infinite age, every finite probability, however small, is realized infinitely many times. Given an infinite future, every fluctuation that is not absolutely forbidden by the laws of physics will happen, not once but infinitely often. This is the Boltzmann brain paradox, named for the Austrian physicist Ludwig Boltzmann, who first grappled with the implications of statistical mechanics applied to an infinite future. A Boltzmann brain is a hypothetical spontaneous quantum fluctuation of sufficient complexity to constitute a mind, a momentary assembly of particles into the configuration required for conscious experience, arising without any evolutionary history or biological context, existing for an instant before dissolving back into the thermal equilibrium from which it fluctuated. The time required for a Boltzmann brain fluctuation to occur by chance in the heat-death universe is unimaginably long, far longer than the black hole era, longer than any number that can be written with conventional notation. But it is not infinite, and in an infinite future universe, it is inevitable. The disturbing implication of Boltzmann brains is not just that they will occur in the far future. It is what they imply about the present. If the universe lasts forever and Boltzmann brains arise with some finite frequency in the heat-death era, then over an infinite future, the total number of Boltzmann brain experiences vastly exceeds the total number of experiences had by observers who evolved through the normal biological and cosmological processes that produced us. If experiences are distributed randomly over observers, and if Boltzmann brains vastly outnumber biological observers, then any given experience is overwhelmingly more likely to be a Boltzmann brain experience than a biological one, which would mean that the odds are overwhelmingly against the hypothesis that you are a biological observer who evolved on a planet in the stelliferous era. The odds say you should be a Boltzmann brain, a momentary fluctuation that happens to have memories of a past that never actually occurred, experience that will end within moments. Most physicists are not Boltzmann brains, or at least they hope not to be, and the discomfort with this implication has motivated serious attempts to find a resolution. Some resolutions involve modifications to cosmology that prevent the universe from persisting in a heat-death state forever, either through vacuum decay that resets the state of the universe periodically, or through a cyclic cosmology in which the heat-death of one universe is the seed of the next. Other resolutions invoke anthropic reasoning, arguing that we find ourselves in the early stelliferous era rather than the heat-death era because the early era is the only time when observers can arise through normal evolutionary processes. Still others argue that the calculation of Boltzmann brain frequency is wrong and that the true rate is zero because quantum gravity effects prevent the necessary fluctuations. None of these resolutions is universally accepted, And the Boltzmann brain problem remains one of the stranger open questions at the intersection of cosmology, quantum mechanics, and philosophy of mind. What the Boltzmann brain problem illustrates is something important about the relationship between the laws of physics and the concept of an ending. The laws of physics do not end at heat death. They continue, and their continuation in a universe of maximum entropy produces consequences that are, by the standards of everything that happened in the previous eras of cosmic history, extremely rare but not zero. The universe after its expiration date is not nothing. It is an infinite future of extreme rarity, in which the ordinary rules about what counts as an event or an object or an experience still technically apply, but apply at frequencies so low that the connection to anything like ordinary existence is tenuous at best. There is another process that the laws of physics permit in the post-expiration universe, and it is more dramatic than Boltzmann brains and potentially more consequential. It is vacuum decay, which we discussed in the context of the quantum vacuum. The possibility that our current vacuum state is metastable, that there exists a lower energy vacuum configuration that our universe could quantum tunnel into, does not disappear at heat death. If our vacuum is metastable, the probability of a tunneling event per unit volume per unit time is a fixed physical constant, determined by the shape of the potential energy landscape of the quantum fields. In a universe that persists forever, the probability of a tunneling event somewhere in the infinite volume of space approaches certainty over an infinite time, regardless of whether that universe is in a stelliferous era or a heat-death state. If vacuum decay occurs in the post-expiration universe, the effect is the same as vacuum decay in any era. A bubble of true vacuum nucleates at some point in space and expands outward at the speed of light, converting the false vacuum of our universe into the true vacuum with its different physical constants. The heat-death universe does not resist this process. There are no structures to be disrupted, no life to be threatened, no observers to notice. The bubble expands through a universe of maximum entropy and converts it to a universe of different physical constants, and whatever those constants support, if they support anything, becomes the new physics. The heat death is not the last state of the universe. It is the last state of the physics we know, and the transition to a different vacuum, if it occurs, is the beginning of something whose nature we cannot determine from our current position inside the metastable vacuum. The question of whether the post-expiration universe gives rise to anything new, whether the quantum fluctuations and the possible vacuum decay lead anywhere, is one that cosmology approaches through the concept of eternal inflation and the multiverse. In inflationary cosmology, the universe we observe is a bubble that nucleated from a background of eternally inflating space, a region that underwent a phase transition from inflationary expansion to the slower expansion of our era, while the surrounding space continued inflating. Other bubbles nucleate elsewhere in the inflating background, each one becoming a universe with potentially different physical constants depending on which vacuum state the inflating region tunneled into when the bubble formed. This is the multiverse of inflationary cosmology, and if it is real, the heat death of our universe is not the end of everything. It is the end of our particular bubble, while the inflationary background from which it nucleated continues spawning new bubbles indefinitely. Whether eternal inflation and the multiverse are real is not currently testable in any direct observational sense. Bubbles in the inflating background are causally disconnected from each other, meaning that no signal can travel from one bubble to another. If we are inside one bubble, the other bubbles are in principle forever outside our causal horizon, and no observation we make inside our bubble can confirm or deny the existence of the others. The multiverse is a theoretical prediction of inflationary cosmology, and inflationary cosmology is supported by the observations of the cosmic microwave background and the large-scale structure of the universe. But the specific prediction of other bubbles with different physics is not directly testable. It is the kind of scientific prediction that is compelling in its theoretical motivation, and its internal consistency, but frustrating in its observational inaccessibility. Roger Penrose's conformal cyclic cosmology, which we discussed at length in the context of our universe's beginning, offers a different picture of what comes after the expiration. In CCC, the heat-death state of our universe and the Big Bang state of the next universe are conformally equivalent geometric objects, meaning that the end of one eon is the beginning of the next. The massless radiation of the heat-death passes through a conformal boundary and becomes the seed radiation of a new Big Bang, and the universe begins again with a new stelliferous era, new stars, new planets, new chemistry, and potentially new life. The cycle is infinite in both directions, with no first universe and no last universe, each ending seeding the next beginning through the geometry of massless radiation and the conformal equivalence of the past and future boundaries of spacetime. CCC makes specific observational predictions about patterns in the cosmic microwave background, the concentric rings of anomalous temperature variance that Penrose and his colleague Gurzadian claim to have found in the WMAP data, and that subsequent analyses have disputed. The debate over whether the CMB contains CCC signatures is ongoing and unresolved, and whether the predictions of CCC are confirmed or ruled out by the current data depends on the specific statistical analysis employed and the interpretation of the results. What is not in dispute is that CCC is a serious theoretical framework based on rigorous mathematics, and that its prediction of a cyclic universe is a genuine physical hypothesis rather than a philosophical speculation. What all of these frameworks share, inflationary multiverse, conformal cyclic cosmology, vacuum decay to a new physics, is a recognition that the expiration date of our universe is not the end of everything. It is the end of the particular configuration of physics and matter and energy that we inhabit, the end of the era in which stars burn and planets form and chemistry organizes into biology and biology into minds. But physics continues. Space continues to expand. Quantum fluctuations continue to occur, and the consequences of physics operating in the post-expiration universe, whatever they turn out to be, are part of the full story of what exists, even if that part of the story is inaccessible to any observer who evolved during the stelliferous era. We are in the stelliferous era. We are, as we noted earlier in the early part of it, closer to the beginning than the end by a factor of roughly 10,000. The universe around us is busy with the business of the burning era, with star formation and stellar death and chemical enrichment, and the slow construction of complexity from the products of nuclear physics. The expiration date, the moment when the last black hole evaporates and the heat death begins, is so far in the future that its relationship to the present is more mathematical than experiential. It is a real date in the calendar of cosmic physics, but it is not a date that affects anything about tonight, or tomorrow, or any timescale relevant to any concern that any living thing in the current universe could reasonably hold. What it does affect is the frame. Understanding that the universe has an expiration date changes the way the present looks, not by making it smaller but by making it more precisely located. We are not in an eternal steady state. We are in a phase that is active and luminous and chemically productive and hospitable to the emergence of complexity in life. A phase that will last for a duration that is effectively infinite by any human measure, but a phase nonetheless, with a beginning and a middle and an eventual end. The end is not tonight, but knowing that it exists, knowing the physics that drives it and the timescales that govern it, gives the present a kind of specificity it would not otherwise have. The stars are burning right now because we are in the era when stars burn. The night sky is full of light right now because we are in the phase of cosmic history that produces light. The atoms in the bodies of every living thing on this planet are the products of stellar deaths that happened in the stelliferous era, synthesized by the nuclear burning that defines this era, and scattered by the supernova deaths that punctuate it. We are not early in an eternal process. We are appropriately located in a finite one, embedded in the only era of cosmic history when the conditions for life and awareness and the capacity to ask questions about the universe are available. That location is worth noticing, not because it is comfortable, though it may be, but because it is specific. The universe will expire. The physics says so with the same certainty with which it says anything. But the universe has not expired yet. The stars are still burning. The night is still full. And whatever comes after the expiration, whatever the infinite future of the post-expiration universe contains, is not available to anything that lives in the stelliferous era and is not relevant to the fact of the night and the fact of the stars and the fact of the mind that looks up at them and tries to understand what they are doing and where they are going. We are going to spend the rest of this night following the physics through each of those eras in more careful detail, because the summary we have been building is incomplete in ways that matter. The specific timescales of the transitions, the specific objects that dominate each era, the specific processes that drive the change from one era to the next, and the specific question of what, if anything, is left after the last black hole evaporates and the universe settles into the quiet that follows its own expiration. The last red dwarfs are worth spending time with before we move through the eras that follow them, because they are the final act of the stelliferous era, and because their nature is so different from the stars we are most familiar with that they deserve their own careful description. Red dwarfs are the most common stars in the Milky Way, making up roughly 70 to 75% of all stellar objects, and they are the most fuel-efficient stars that exist. Where the sun converts its hydrogen to helium in a core that occupies roughly 10% of its radius, mixing new fuel into the burning region only slowly, and leaving a growing helium ash in the center, red dwarfs are fully convective. The entire star is in a state of continuous mixing, with material from the outer layers being circulated through the core and back out again in a continuous convective overturn that lasts the entire stellar lifetime. This means that a red dwarf does not accumulate a helium core. It burns its hydrogen fuel uniformly throughout its interior, converting essentially all of its hydrogen to helium before the fuel is exhausted rather than just the central fraction. The result is a stellar lifetime that is dramatically longer than the sun's. The sun will live for approximately 10 billion years on the main sequence. A red dwarf with half the sun's mass will live for roughly 80 billion years. A red dwarf with a third of the sun's mass will live for several hundred billion years. The smallest red dwarfs, those with masses around 8% of the sun's mass, the minimum required for sustained hydrogen fusion, will burn for roughly 10 trillion years. 10 trillion years is 1,000 times the current age of the universe. The last of these smallest red dwarfs will still be burning when the universe is 1,000 times older than it is today. They are the final embers of the stelliferous era, burning quietly in what will by then be an otherwise dark galaxy. Their light the last stellar light in a universe that was once full of it. As a red dwarf approaches the end of its fuel supply, it does not undergo the red giant expansion that characterizes the death of more massive stars. Red dwarfs do not have the mass required to ignite helium fusion after the hydrogen is exhausted, and they do not have the structural complexity of a separate core and envelope that drives the red giant expansion in solar-type stars. Instead, as the hydrogen fuel runs low, the red dwarf simply becomes less luminous and smaller, contracting gradually and cooling, passing through a blue dwarf phase as it heats and shrinks before the fusion finally ceases entirely. It does not shed a planetary nebula. It does not produce a nova or supernova. It simply fades over timescales of trillions of years, from a dim red star to a dim blue star, to a cooling white dwarf that is somewhat less massive than the white dwarfs produced by solar-type stars. The white dwarfs produced by red dwarfs are therefore the last white dwarfs to form in the galaxy, appearing in the universe when it is hundreds of billions to trillions of years old, after every more massive star has long since completed its life cycle and produced its own white dwarf or neutron star or black hole. They join a population of white dwarfs that includes the remnants of every star that has ever lived and died in the galaxy, accumulated over the entire history of stellar formation, and spanning the full range of possible white dwarf masses and compositions. The oldest white dwarfs in the galaxy today are approximately 13 billion years old, already cool enough that they have fallen below the detection threshold of current observational surveys. The white dwarf that our Sun will leave behind in 5 billion years will cool for trillions of years after that. And the white dwarfs produced by the last red dwarfs, forming in the universe when it is 1 trillion years old, will cool for even longer. The cooling of a white dwarf is a process that proceeds through several phases, each characterized by different physics and different observable properties. In the early cooling phase, when the white dwarf is still hot, the dominant energy loss is from photon radiation from the surface, and the cooling rate is governed by the opacity of the outer layers to radiation transport. As the temperature drops below roughly 12,000 degrees Kelvin, the ions in the interior of the white dwarf begin to crystallize, forming a solid lattice of carbon and oxygen ions suspended in a sea of degenerate electrons. This crystallization releases latent heat, briefly slowing the cooling rate in a way that produces a characteristic feature in the luminosity distribution of observed white dwarfs, a pileup of white dwarfs at a specific temperature range corresponding to the crystallization phase. The Gaia Space Telescope has detected this feature in the white dwarf population of the Milky Way, providing direct observational confirmation that white dwarfs are crystallizing. After crystallization, the cooling continues at a rate governed by the heat capacity of the crystalline lattice and the thermal conductivity of the degenerate electrons. At very low temperatures, quantum effects become important in the lattice, reducing the heat capacity below the classical value in a way described by the Debye model of lattice heat capacity. This Debye cooling regime means that as the temperature approaches absolute zero, the cooling rate slows dramatically. The white dwarf asymptotically approaches absolute zero, but never quite reaches it, losing heat more and more slowly as its temperature drops. The result is that white dwarfs cool very rapidly at first, when they are hot and radiating efficiently, and then more and more slowly as they cool, with the last few degrees of cooling taking longer than all the previous cooling combined. This behavior means that even the oldest white dwarfs in the universe today are still measurably warm. The coolest observed white dwarfs have temperatures of roughly 3,000 to 4,000 degrees Kelvin, still warm enough to glow faintly in the infrared, still carrying detectable heat from the nuclear burning that produced them billions of years ago. By the time the universe is 100 times its current age, these oldest white dwarfs will have cooled to temperatures of perhaps a few hundred degrees, warm enough that the distinction between them and the surrounding space becomes increasingly difficult to measure. Eventually, they will cool to temperatures indistinguishable from the cosmic microwave background, at which point they become completely invisible to any thermal observation, and their presence can only be inferred gravitationally. In the far future, long after the last white dwarfs have cooled below any thermally detectable temperature, the physics of the white dwarf interior changes in ways that are slow even by the standards of the degenerate era. The crystalline lattice of carbon and oxygen nuclei is not the lowest energy configuration available to the matter in a cold white dwarf. The lowest energy configuration, from the perspective of nuclear binding energy, is pure iron. Carbon and oxygen nuclei are less tightly bound per nucleon than iron nuclei, and in principle the white dwarf could lower its energy by converting its carbon and oxygen to iron through nuclear reactions. In practice, this conversion is blocked by the same electrical repulsion between nuclei that prevents fusion in ordinary conditions. But quantum tunneling allows nuclei to pass through this barrier with a probability that is finite, however small, and over a long enough time, tunneling-driven nuclear reactions will convert the entire white dwarf from a mixture of carbon and oxygen to pure iron. The timescale for this conversion is approximately 10 to the power of 1,500 years. This number is not a mistake. It is not 10 to the power of 15, which would be a quadrillion years. It is 10 to the power of 1,500, a 1 followed by 1,500 zeros. This number is so large relative to the other large numbers in the story of the universe's fate that it occupies a different category entirely. The evaporation of the largest supermassive black holes takes 10 to the power of 100 years, which seems enormous. The quantum tunneling conversion of a white dwarf to iron takes 10 to the power of 1,500 years, which is 10 to the power of 1,400 times longer. The iron conversion of white dwarfs is one of the most delayed processes that the known laws of physics permit, and it happens to every cold white dwarf, given infinite time. After the iron conversion, the white dwarf is a cold sphere of iron at a density maintained by degenerate electron pressure, containing roughly a solar mass of material in a volume the size of the Earth. It is the most stable form that ordinary matter can take in bulk at low temperature, the nuclear ground state of macroscopic matter. It is also completely dark, completely cold, and completely inert. It is as close to nothing as a solar mass of matter can get while still being a solar mass of matter. And in an infinite universe, there will eventually be many of these iron spheres drifting through the cold and dark of the far future, the final transformation of every white dwarf that ever formed, the nuclear ground state of the material that was once the hearts of burning stars. Whether this transformation occurs before or after proton decay depends on whether protons are stable. If proton decay proceeds at the rate predicted by grand unified theories, roughly 10 to the power of 36 years, then the white dwarfs dissolve long before the quantum tunneling conversion has time to occur. The protons in the carbon and oxygen nuclei of the white dwarf decay individually, converting to positrons and pions that then decay further, releasing energy as gamma rays and neutrinos. The decay of protons in a white dwarf is not explosive. It is a slow trickle of energy, one proton at a time, spreading outward from wherever in the white dwarf the decay occurs. The energy released by each decay is absorbed by the surrounding material and re-radiated as thermal photons, giving the decaying white dwarf a faint glow of thermal radiation powered entirely by the decay of its constituent protons. This proton decay luminosity is tiny by stellar standards. A solar mass white dwarf decaying through proton decay at the theoretically predicted rate has a luminosity of roughly 400 watts, comparable to a few incandescent light bulbs. This is not visible at any significant distance with current instruments, but it is not zero, and in the deep dark of the degenerate era, it represents a genuine and detectable source of radiation in an otherwise lightless universe. Proposed experiments to detect proton decay by looking for the characteristic radiation from decaying white dwarfs in the far future are one of the more whimsical thought experiments in theoretical physics, since no observer is expected to exist to conduct such an experiment. But the calculation can be done, and the answer is that a white dwarf decaying through proton decay is faintly luminous for roughly 10 to the power of 37 years before all its protons have decayed, and it dissolves into a dilute cloud of positrons, electrons, neutrinos, and radiation. The proton decay experiments currently operating on Earth, deep underground tanks of water, or other materials monitored for the characteristic Cherenkov radiation produced by proton decay products, have not detected a single proton decay in decades of operation. This places a lower bound on the proton lifetime of roughly 10 to the power of 34 years, already at the edge of the range predicted by the simplest grand unified theories. The non-detection has ruled out the most minimal grand unified theories and placed constraints on more complex ones. Whether protons are stable over truly infinite timescales, or whether they decay on timescales of 10 to the power of 40 or 50 or 100 years rather than 34 to 36, is a question that current experiments cannot answer. The answer matters for the details of the degenerate era, but not for its ultimate outcome. Whether ordinary matter dissolves through proton decay or through quantum tunneling conversion to iron, it eventually disappears from the cosmic inventory, leaving only the black holes. The black holes of the black hole era span an enormous range of masses, from a few solar masses for the remnants of individual stellar deaths to billions of solar masses for the supermassive black holes that grew at the centers of galaxies throughout the stelliferous era. This mass range corresponds to an enormous range of Hawking temperatures and evaporation timescales. The smallest black holes, stellar mass remnants of a few solar masses, have Hawking temperatures of tens of billionths of a degree and evaporate in roughly 10 to the power of 67 years. The most massive supermassive black holes, with masses of tens of billions of solar masses, have Hawking temperatures of tens of trillionths of a degree and evaporate in roughly 10 to the power of 100 years. The range in evaporation timescales across the black hole mass spectrum is itself enormous, a factor of roughly 10 to the power of 33 between the smallest and largest. During the black hole era, the black holes are not merely sitting still and slowly evaporating. They continue to interact with their environment, however sparse that environment has become. Occasional particles from the thermal background drift close enough to be absorbed, adding infinitesimal mass. The gravitational wave background, still propagating from the earlier eras, carries energy past the black holes without interaction. In binary black hole systems that have not yet merged, the gravitational wave emission from the orbiting pair continues to drain energy from the orbit and bring the two closer together, eventually driving a merger that produces a single more massive black hole and a burst of gravitational waves. These merger events become increasingly rare as the universe ages, and the black hole population becomes more dispersed by the overall expansion of space, but they continue to occur for as long as gravitationally bound pairs exist. The gravitational wave bursts from black hole mergers in the black hole era are among the most energetic events in the post-stelliferous universe. A merger of 2 billion solar mass black holes releases gravitational energy comparable to the total energy output of the entire Milky Way over its entire stelliferous era history, radiated in a few hours or days of inspiral and merger. In the empty, cold, dark universe of the black hole era, such an event is the most dramatic thing that can happen, and it happens in complete isolation, with no electromagnetic counterpart, no optical flash, no kilonova. Just the ripple of spacetime spreading outward from the merger at the speed of light, carrying information about the mass and spin of the merging black holes to a universe that has no instruments to receive it and no observers to care. The evaporation of individual black holes through Hawking radiation accelerates as the mass decreases. For most of the evaporation lifetime, the process is extraordinarily slow. A 10 solar mass black hole spends the vast majority of its evaporation time, roughly 99.9% of it, at temperatures below a millionth of a degree, radiating photons with wavelengths longer than the diameter of the solar system. This radiation carries essentially no information that would be detectable by any instrument, and contributes an utterly negligible amount of energy to the surrounding universe. The black hole is effectively frozen in this phase, changing imperceptibly over timescales that make the stelliferous era look instantaneous. As the mass drops below roughly 10 billion kilograms, the temperature rises to the point where the Hawking radiation becomes energetic enough to produce electron-positron pairs in addition to photons. The radiation is still cold by stellar standards, but it is beginning to heat up rapidly because the temperature inversely tracks the mass, and the mass is now dropping faster. Below roughly 1 million kilograms, the temperature exceeds the mass energy of protons and neutrons, and the Hawking radiation begins to include baryons, hadrons, and a full spectrum of standard model particles. The final stages of black hole evaporation are the hottest and most energetic phase, with the temperature climbing through billions, trillions, and eventually quadrillions of degrees in the last fractions of a second. The final evaporation of a black hole is a burst of high-energy radiation and particles that lasts for a fraction of a second and releases the remaining mass energy of the black hole at temperatures that have not existed in the universe since the first moments after the Big Bang. For a stellar mass black hole, the final burst has a peak energy roughly comparable to a large nuclear weapon, released in a volume smaller than an atomic nucleus. For a supermassive black hole, the final burst is correspondingly more energetic. The radiation from the final burst propagates outward through the dark and empty universe, gradually redshifting and cooling as the expansion of space stretches its wavelengths. It joins the diffuse radiation bath of the dark era, adding an infinitesimal contribution to the thermal background that is all that remains after the last structure has dissolved. The information paradox, which we discussed in the context of Hawking radiation in the star death video, is most acute at this final moment. If the Hawking radiation carries no information about what formed the black hole, then the information about the entire history of everything that ever fell into the black hole is lost in the final evaporation. A black hole that formed from the collapse of a massive star and then spent 10 to the power of 67 years accreting material from the surrounding universe, accumulating matter and radiation from billions of stellar generations, would evaporate into a burst of thermal radiation indistinguishable from the thermal radiation produced by a black hole of the same final mass, formed from any other combination of materials. If this is true, and if quantum mechanics is correct that information must be conserved, then the evaporation process must somehow encode the entire accumulated history of the black hole in the correlations of the emitted Hawking photons, in a way that is computationally accessible in principle, but practically unrecoverable in any realistic sense. The current theoretical consensus, as we mentioned, is that information is preserved in the Hawking radiation in a subtle and highly scrambled form. The argument for this, developed through the work of Hawking and Maldacena and Polchinski, and many others in the context of the information paradox debates, involves the holographic principle and the idea that the quantum state of the black hole interior is encoded in the correlations of the Hawking photons in a way that makes the radiation appear thermal locally, but carry information globally. Extracting the information from the radiation would require a computation of extraordinary complexity, essentially the quantum analog of unscrambling an egg, but the information would in principle be there. The black hole does not destroy information. It scrambles it thoroughly and returns it to the universe in a form that is effectively unreadable. Whether this theoretical consensus is correct will not be determined observationally, at least not from within our current universe. The Hawking radiation from any black hole accessible to observation is far too cold and far too faint to detect with current or foreseeable technology, and the specific correlations that would encode the information are so subtle and so non-local that even in principle their detection would require the ability to measure the quantum state of every photon in the radiation simultaneously, an experiment that is not physically realizable. The information paradox is likely to remain unresolved observationally and may be resolved only theoretically, through the development of a complete and consistent theory of quantum gravity that makes the information preservation mechanism explicit. After the last black hole evaporates, the universe enters the dark era. This is the state of maximum entropy, the closest the universe can get to the heat death that thermodynamics predicts. The universe is not perfectly uniform in the dark era, because quantum fluctuations are still occurring and gravitational waves are still propagating, and the relic radiation is still present with tiny temperature fluctuations from the era of structure formation. But it is as close to uniform as the physics permits. There are no structures, no concentrations of matter or energy, no gradients that could drive a spontaneous physical process. The laws of thermodynamics say that spontaneous processes require free energy, and the dark era universe has none. Everything that can happen spontaneously has happened. The entropy has reached its maximum. Except that quantum mechanics does not fully agree with thermodynamics about what spontaneous means. Thermodynamics is a classical theory, a theory of large systems with many degrees of freedom, and its predictions about what can and cannot happen spontaneously are statistical rather than absolute. The second law of thermodynamics says that entropy increases in a closed system on average, not that it increases in every possible instance. In a system of a finite number of particles in a finite volume, the entropy can fluctuate downward spontaneously, with a probability that decreases exponentially with the size of the fluctuation. The Poincare recurrence theorem, which applies to any system with a finite number of degrees of freedom, evolving according to deterministic equations, says that any such system will eventually return arbitrarily close to any previous state, given enough time. The recurrence time is unimaginably long for any macroscopic system, but it is finite, and in an infinite future it is inevitable. The dark era universe, if it is finite in some effective sense, or if it has a finite number of accessible degrees of freedom in any given region, is subject to Poincare recurrence in principle. The recurrence time for the entire observable universe is a number so large that no standard notation can express it without resorting to Tower exponentials, numbers of the form 10 to the power of 10 to the power of 10, stacked recursively to heights that strain the concept of a number. But it is finite, and in an infinite future, the universe will spontaneously fluctuate back to any previous configuration, including configurations with burning stars and living planets, infinitely many times. The dark era is not the final silence. It is the background against which the infinite future plays out, punctuated by quantum fluctuations of every possible size and complexity, from single particle pair productions to entire universes spontaneously fluctuating into existence from the thermal background. The Boltzmann brain problem, which we introduced in the first part of tonight's discussion, arises from this picture. In an infinite future of Poincare recurrences, the most common fluctuations that produce an observer are not the ones that produce an entire coherent universe with a consistent history, full of galaxies and stars and planets and evolving life, because these fluctuations require an enormous coincidence of initial conditions. The most common observer-producing fluctuations are the minimal ones, the smallest fluctuation capable of producing a momentary conscious experience. These minimal observers, these Boltzmann brains, are vastly more common in the infinite future than the organized biological observers that arise through the normal processes of the stelliferous era. If observers are randomly distributed over the infinite future, then the overwhelming majority of all observers that ever exist in the history of the universe, including its infinite future, are Boltzmann brains. And if you are equally likely to be any observer, then you are overwhelmingly likely to be a Boltzmann brain. The implications of this reasoning have been taken seriously enough that several proposed resolutions to the cosmological constant problem and the fine-tuning of the universe's initial conditions have been constrained or rejected on the grounds that they predict too many Boltzmann brains. A cosmological model that predicts more Boltzmann brain observers than biological observers is considered internally inconsistent because it predicts that the conditions of its own derivation, the existence of scientists doing cosmology in an organized universe, are overwhelmingly improbable. This is a strange kind of self-referential constraint on cosmological models, but it is taken seriously because the alternative, accepting that we are probably Boltzmann brains, seems to undermine the entire enterprise of cosmological reasoning. The most natural resolution of the Boltzmann brain problem, within the framework of modern cosmology, is eternal inflation. If the universe is eternally inflating, with new bubble universes nucleating continuously from the inflating background, then the relevant measure is not over the infinite future of a single universe, but over the entire ensemble of bubble universes and their temporal histories. In this picture, the Boltzmann brain problem is resolved if the rate of biological observer production across the ensemble of bubble universes exceeds the rate of Boltzmann brain production, which requires that the physics of the bubble universes be such that they produce enough organized structure and enough observers before heat death to outweigh the Boltzmann brains produced in the infinite future of each bubble. Whether the specific physics of our universe satisfies this condition is a calculation that has not been definitively completed, partly because the measure problem in eternal inflation, the question of how to count observers across an infinite ensemble of universes, is itself unresolved. Another proposed resolution involves a modification of the cosmological constant problem that prevents the universe from existing in a heat-death state for an infinite time. If the vacuum of our universe is metastable and undergoes a decay to a new vacuum with different physical constants on some finite timescale, then the dark era of our universe has a finite duration, bounded above by the vacuum decay timescale. The Boltzmann brains that would accumulate in an infinitely long dark era do not have infinite time to accumulate if the dark era is finite. Whether the vacuum decay timescale is short enough to prevent Boltzmann brain domination is a question that depends on the specific shape of the vacuum potential, which is not fully constrained by current physics. Penrose's conformal cyclic cosmology resolves the Boltzmann brain problem differently. In CCC, the heat-death state of our universe is not a permanent endpoint, but a transition to the next eon. The dark era does not persist forever. It ends, conformally, at the moment when the last massive particles have either decayed or been absorbed into black holes that then evaporate, leaving a universe of only massless radiation that is conformally equivalent to a Big Bang. The next eon begins, new structure forms, new observers arise through normal biological processes, and the Boltzmann brain problem does not arise because the dark era is finite. Whether CCC is the correct picture of what happens after heat death is unknown, and its observational predictions remain contested. But it is a consistent framework that resolves several of the deepest puzzles in cosmology simultaneously, which is a point in its favor, even in the absence of confirmed observational support. The question of what the universe is doing right now, in the context of these far future considerations, is worth asking directly. We are in the stelliferous era. We are observing a universe full of burning stars, cooling white dwarfs, spinning neutron stars, and accreting black holes. The physics we observe is the physics of the era of maximum structural complexity, the era in which matter has organized itself through gravity and nuclear physics and chemistry into the richest variety of objects and processes that the universe has ever produced or will ever produce. The degenerate era will be simpler. The black hole era will be simpler still. The dark era is the simplest of all. We are at the peak of cosmic complexity, and the rest of the universe's history is a long decline toward simplicity. This decline is built into the laws of physics. Entropy increase is not a temporary phenomenon. It is the direction of time itself, and the universe is moving in that direction at every moment, in every process, at every scale. The complexity we see around us, the stars and planets and life and minds, is not a violation of this trend but a local eddy within it, a temporary and improbable concentration of low entropy sustained by the ongoing flow of energy from the sun, and ultimately from the gravitational energy of the Big Bang's initial conditions. The eddies are real, and they matter. The concentration of low entropy in a mind capable of thinking about the universe's fate is one of the most remarkable things the second law of thermodynamics has accidentally produced. But the second law is patient, and it will eventually win, and what it leaves behind when it wins is the dark era. Understanding this is not a counsel of despair. It is a description of the actual situation, which is that we are temporary eddies in a one-way flow, complex enough to understand the flow and temporary enough that the understanding will not persist forever. The universe does not owe us permanence. The laws of physics do not make exceptions for minds. What they give us is time, a finite but enormous amount of it by any human measure, in the only era of cosmic history when the conditions for minds exist. The expiration date is real. It is also so far away that its reality changes nothing about the present except the frame. Frame, though, is worth having. Knowing that the universe will expire, knowing the timescales and the mechanisms, knowing what the physics says about the infinite future after the expiration, is a different kind of knowledge from the ordinary knowledge of the stelliferous era. It is knowledge that places the present in its largest possible context, that locates the burning stars and the warm planets and the living things in the full sweep of what the universe is doing and where it is going. The stars are burning now. The stelliferous era is in progress. The expiration date is written in the physics, but it is not tonight. And knowing that it exists does not make tonight any less the night that it is, full of the light of burning stars and the cold of the space between them and the quiet of the hours when the day has finished, and the universe is as available as it gets. The frame changes everything about how you look at the present without changing anything about the present itself. This is one of the more subtle gifts that cosmology offers, and it is worth unpacking carefully before we turn to the question of what the current observations actually say about which version of the far future is the correct one. The gift is this: knowing that the universe has a fate, knowing the timescales and the mechanisms and the endpoint, does not diminish the present. It locates it. The difference between a universe whose fate is unknown and a universe whose fate is understood is the difference between wandering in a landscape you cannot read and standing in that same landscape with a map. The landscape has not changed. Your ability to be in it has. Most people who think about the end of the universe at all think about it in terms of what will be lost. The stars will go out. The planets will dissolve. Life will end. The mind that asks questions about the universe will eventually not exist. All of this is true, and none of it is comfortable in the conventional sense. But it is the wrong frame for what knowing the fate of the universe actually gives you. What it gives you is not a reason to mourn what will eventually be lost. It gives you a reason to notice what currently exists, which is different. The stars are burning right now. The planets are warm right now. Life is here right now. The mind asking the questions is present right now. Knowing that these things are temporary makes them more specifically located in time, not less real. They are happening in the stelliferous era, in the one phase of cosmic history when such things can happen, and that specificity is more meaningful than a vague sense of permanence would be. This is the frame that cosmology offers and that most discussions of the universe's fate fail to make explicit. The expiration date is not a threat, it is context. And the context is one in which the present is revealed as something that could only have happened in a specific era, of a specific kind of universe. Something that is not guaranteed by the laws of physics, but is produced by a specific combination of initial conditions and constants and cosmic history that led to this particular stelliferous era with its particular population of stars and its particular collection of warm rocky planets and its particular instances of self-aware matter looking up at the sky. But before we can fully inhabit this frame, we need to know which version of the far future the observations actually support. The heat-death scenario we have been describing, the orderly progression through the stelliferous era and the degenerate era and the black hole era and the dark era, is not the only physically possible fate of the universe. The fate depends critically on the behavior of dark energy, the component of the universe's energy budget that is currently driving the accelerating expansion. If dark energy is exactly a cosmological constant, a fixed energy density of empty space that does not change over time, then the future of the universe proceeds approximately as we have described. But if dark energy is something more dynamic, something whose energy density changes over time, then the future could be very different, and the differences are not minor adjustments to the timeline. They are categorically different kinds of ending. The current observational evidence for dark energy comes primarily from two independent lines of measurement that both point to an accelerating expansion. The first is the Type Ia supernova distance scale, which we discussed in the stellar death video. Type Ia supernovae have a standardizable peak luminosity that allows them to be used as distance indicators, and the distances to high redshift supernovae are larger than they would be in a universe with no dark energy, indicating that the expansion has been accelerating. The second line of evidence is the combination of the cosmic microwave background anisotropies and the large-scale structure of galaxy clustering, which together constrain the overall geometry and energy content of the universe. Both measurements are consistent with a universe in which roughly 68% of the total energy content is dark energy, roughly 27% is dark matter, and roughly 5% is ordinary matter, and in which the dark energy behaves like a cosmological constant to within current measurement precision. The phrase "to within current measurement precision" is the crucial qualifier. The cosmological constant is one possible form of dark energy, but it is not the only one. A more general form of dark energy is described by an equation of state parameter, conventionally called W, which specifies the ratio of the pressure to the energy density of the dark energy. For a cosmological constant, W is exactly -1. For other forms of dark energy, W can be different from -1 and can potentially vary over time. The current measurements of W from the combination of supernova, CMB, and large-scale structure data are consistent with W equal to -1. But they allow a range of values from roughly -1.3 to -0.7 at current precision. This range includes not just the cosmological constant, but a variety of other dark energy models, and the consequences of those models for the far future differ dramatically. If W is greater than -1, meaning the dark energy has a weaker repulsive effect than the cosmological constant, the expansion accelerates but at a rate that is bounded. Eventually, the expansion rate approaches a constant value determined by the dark energy density. The galaxies beyond the local group recede past the horizon, and the universe proceeds to heat death on the timeline we have described. This is the standard scenario. If W is exactly -1, as the cosmological constant implies, the behavior is the same as the previous case. The expansion accelerates at a rate that is constant, the horizon grows at a fixed rate, and the universe proceeds to heat death. If W is less than -1, a possibility called phantom dark energy, the situation is more dramatic. Phantom dark energy has an energy density that increases over time as the universe expands, rather than remaining constant. This means the expansion rate does not approach a limit, but continues to accelerate without bound. The expansion rate grows faster and faster, and eventually the expansion becomes so rapid that even structures held together by gravity, then by electromagnetic forces, then by nuclear forces, are ripped apart by the accelerating expansion of the space between their constituent particles. This catastrophic scenario is called the Big Rip, and it ends the universe not with a quiet cooling toward maximum entropy, but with a violent tearing apart of all structure at every scale, culminating in the dissolution of spacetime itself in a finite time. The Big Rip timescale, if phantom dark energy is the correct description, depends on the value of W for W equal to -1.5. The Big Rip occurs in roughly 17 billion years from now. For values of W closer to -1, the Big Rip occurs further in the future, approaching infinite time as W approaches -1 from below. If W is -1.1, for example, the Big Rip does not occur for many trillions of years, far beyond any timescale relevant to stellar evolution or planetary habitability. The observational constraint that W is between roughly -1.3 and -0.7 covers a range that includes both the cosmological constant and mild phantom dark energy. So the Big Rip cannot currently be ruled out, but the values of W required for a Big Rip in the cosmologically near future are excluded by the data. There is a third possibility, one that was considered the most likely scenario before the discovery of dark energy in 1998. If the universe had no dark energy, or if the dark energy were negative rather than positive, the expansion of the universe would be decelerating under the gravitational attraction of its matter content, and the universe could eventually recollapse into a big crunch, a reversal of the Big Bang in which all matter and radiation converge on a single point of infinite density. The Big Crunch was once considered a plausible or even likely fate of the universe, and the question of whether the universe was open, flat, or closed, corresponding to perpetual expansion, marginally perpetual expansion, or eventual recollapse, was one of the central observational questions of 20th century cosmology. The discovery of the accelerating expansion in 1998 resolved this question observationally. The universe is not decelerating, it is accelerating. The Big Crunch is not the fate of the universe, at least not under the current dark energy conditions. However, the Big Crunch has returned as a theoretical possibility through a different mechanism, one that does not require the dark energy to be negative, but that involves a phase transition in the dark energy itself. If dark energy is not a fundamental constant of nature, but rather a field that can transition between different values, it is possible that the universe could undergo a transition in which the dark energy becomes strongly negative, driving a rapid recollapse rather than an accelerating expansion. This scenario, sometimes called a Big Crunch from vacuum decay, is distinct from the classical Big Crunch in that it arises not from the gravitational attraction of matter, but from a fundamental change in the vacuum energy of the universe. Whether such a transition is possible depends on the properties of the dark energy field, which are not currently constrained to the level required to rule it out. The new observations that are most relevant to constraining the dark energy equation of state and the far future of the universe are coming from a new generation of large-scale surveys. The Dark Energy Spectroscopic Instrument, DESI, began operations in 2021 and is measuring the redshifts of tens of millions of galaxies to map the large-scale structure of the universe with unprecedented precision. In 2024, the DESI collaboration released their first cosmological results from the instrument, and the results attracted significant attention because they showed a slight preference, at roughly 2 to 3 sigma statistical significance, for a dark energy equation of state that deviates from the cosmological constant. Specifically, the DESI data, combined with CMB and supernova data, showed a preference for a value of W that varies over time, being somewhat above -1 in the recent past and somewhat below -1 in the earlier universe. This preference is not statistically significant enough to constitute a confirmed deviation from the cosmological constant, and it is consistent with the known systematic uncertainties in the measurements. But it is interesting, and it has motivated theoretical work on dynamical dark energy models that might explain such a variation. The Euclid Space Telescope, launched in 2023 by the European Space Agency, is conducting a survey of the distribution of galaxies and the weak gravitational lensing of their light by large-scale structure across a large fraction of the sky and to high redshift. Euclid is designed specifically to measure the dark energy equation of state with sufficient precision to distinguish between a cosmological constant and dynamical dark energy models at a level of significance that would constitute a confirmed detection. The first science data from Euclid began being released in 2024, and the full survey, which will take several years to complete, is expected to provide the most precise constraints on dark energy ever obtained. If the DESI hint of dynamical dark energy holds up in the Euclid data, it would be one of the most significant discoveries in cosmology since the original detection of the accelerating expansion. The Nancy Grace Roman Space Telescope, formerly known as WFIRST, planned for launch in the late 2020s, will complement Euclid with a different observational strategy, using Type Ia supernovae and weak gravitational lensing to constrain dark energy. The combination of Roman, Euclid, and Daisy data over the next decade will provide the most detailed picture of the dark energy equation of state ever assembled, potentially resolving whether W is constant or varying, and if varying, how it varies over cosmic time. The fate of the universe in its broadest sense, whether it ends in heat death or big rip or something more exotic, depends on the answer to this question, and the answer is currently within the reach of ongoing observational programs. Beyond dark energy, there is another cosmological measurement with profound implications for the far future: the Hubble tension. The Hubble constant, the rate at which the universe is currently expanding, can be measured in two fundamentally different ways. One way is to use the CMB and the Standard Model of Cosmology to infer the expansion rate from the physics of the early universe, extrapolated to the present. Another way is to measure the expansion rate directly using distance indicators in the local universe, including Type Ia supernovae, calibrated by Cepheid variable stars, and other distance ladder methods. These two measurements have been giving different answers for several years, with the CMB-based value being roughly 67 kilometers per second per megaparsec, and the local distance ladder value being roughly 73 kilometers per second per megaparsec, a discrepancy of roughly 9% that exceeds the individual measurement uncertainties by several sigma. This Hubble tension is not directly relevant to the far future of the universe in any specific way, but it matters because it suggests that something may be wrong with the standard cosmological model, and the standard cosmological model is what we use to predict the far future. If the tension is resolved by modifying the dark energy model, or by adding new physics to the early universe, or by some systematic error in one of the measurement methods, the implications for the far future differ. A modification of dark energy that resolves the Hubble tension by making dark energy more dynamical would also modify the predicted timeline of the far future. A resolution through early universe physics would leave the far future predictions unchanged. The Hubble tension is therefore a clue about the possible incompleteness of the Standard Model, and its resolution may or may not turn out to be relevant to the fate of the universe. What the current observational situation amounts to is this: we have strong evidence that the universe is expanding, and that the expansion is accelerating. We have strong evidence that approximately 68% of the universe's energy content is in the form of dark energy, and we have measurements of the dark energy equation of state that are consistent with a cosmological constant, but allow for dynamical models within the current uncertainties. The heat death scenario is the most likely outcome given the current data, but it is not the only possible outcome, and improvements in dark energy measurements over the next decade will significantly reduce the uncertainty. The universe's expiration date is known to within the constraints of our current understanding of dark energy, and those constraints are about to become much tighter. There is a question that sits underneath all of this observational discussion, and it is a philosophical one rather than a physical one, but it is worth asking because it changes the texture of what knowing the fate of the universe means. The question is, why does it matter that the universe has an expiration date, given that the expiration date is so far in the future that it has no conceivable effect on anything that anyone in the current era could experience or care about? The honest answer to this question has several layers. The first layer is scientific. The fate of the universe is a prediction of the physical theories we use to describe it, and the accuracy of that prediction is a test of those theories. A theory that correctly describes the expansion history of the universe, the formation of large-scale structure, the properties of the cosmic microwave background, and the behavior of dark matter and dark energy across the observable universe should also make correct predictions about the universe's future. The far future is simply the logical extension of the physics we test in the present. Testing the physics of the present more precisely is therefore also, in a specific and rigorous sense, testing predictions about the far future. The second layer is mathematical. The equations of cosmology do not stop applying at any particular time. They describe the evolution of the universe from the Big Bang to the infinite future, and the solutions of those equations in the far future are as much a part of the mathematical content of the theory as the solutions in the present. Ignoring the far future solutions on the grounds that they are too distant to matter practically would be like ignoring the behavior of a mathematical function at infinity on the grounds that you only care about its values in a finite range. The behavior at infinity is often what reveals the most fundamental properties of the function, and the behavior of the universe in the far future reveals properties of the physical laws that govern it that are not apparent in the short-term solutions. The third layer is existential, and it is the one that is most relevant to why the expiration date matters for anything beyond academic physics. The universe having an expiration date means that the conditions for life and complexity and awareness are not permanent features of reality but temporary ones, specific to an era of cosmic history that is occurring now and that will eventually end. This is the same truth that applies to every individual life, but applied at the largest possible scale. The universe will end as every living thing ends, not in destruction but in dissolution, in the return of its organized complexity to the ground state of simplicity from which it arose. The parallel is not an analogy. It is the same physical process, the second law of thermodynamics, operating at the scale of an individual organism and at the scale of the entire universe, with only the timescales differing. What this parallel offers is a kind of perspective that is available only to minds that can hold both scales simultaneously, that can think about their own mortality and the mortality of the universe in the same thought and notice that they are the same kind of thing. This is not a comfortable perspective in any conventional sense, but it is an honest one. The universe is mortal. We are mortal. The mortality is written into the same laws of physics that make us possible. And knowing this, really knowing it rather than holding it at arm's length as an abstract fact about distant timescales, changes the quality of attention you can bring to the present. The present is the stelliferous era. The present is the only era of cosmic history when burning stars provide the energy gradients that sustain complex chemistry and biology in minds. The present is the era when the entropy gradient between the hot sun and the cold sky allows the Earth's biosphere to maintain its organized complexity against the second law's constant pressure toward disorder. The present is the era when the products of stellar death, scattered across the galaxy over billions of years, have accumulated in sufficient quantity and variety to build rocky planets with the chemical complexity required for life. The present is the era when all of this is happening simultaneously, in a universe that is 13.8 billion years into the stelliferous era and has not yet reached the midpoint of it. We are, in the most specific physical sense, living in the sweet spot, not the sweet spot of some designed plan or intentional arrangement, but the sweet spot that the physics produces given the initial conditions and the constants and the history that have led to now. The sweet spot where entropy has increased enough from the Big Bang's initial low entropy state to allow the formation of complex structures, but not so much that those structures have dissolved back into uniformity. The sweet spot where the universe is old enough for the chemical enrichment of multiple stellar generations to have occurred, but young enough that stars are still burning and planets are still forming. The sweet spot where dark energy has not yet pushed all structure beyond the horizon, but the horizon has already retreated enough to reveal the full scale of the cosmic web. The sweet spot where the laws of physics have had enough time to produce minds capable of understanding those laws, but not so much time that those minds have dissolved along with everything else. The expiration date makes the sweet spot visible, Without it, the present would look like a permanent condition, a default state of the universe rather than a specific phase in its history. With it, the present is revealed as what it actually is, a window. Not the only window, not the last window, but the one that is currently open, the one through which everything that we call experience and knowledge and awareness is currently passing. The window will close. The physics says so with certainty. But the window is open right now, and the universe is as available as it will ever be to the kind of thing that looks through windows and wonders what is on the other side. The next generation of cosmological surveys will tell us more precisely when the window closes and what the closing looks like, whether the heat-death proceeds on the classical timeline or whether dark energy is dynamical in ways that change the schedule. The Dacey and Euclid results over the next decade will refine the expiration date, not to the nearest year, but to the nearest order of magnitude in the enormous exponents that describe it. They will tell us whether W is exactly -1 or deviates from it, and if it deviates, in which direction and by how much. They will tell us whether the Big Rip is a possibility we need to take seriously, or whether the expansion is bounded in a way that guarantees the classical heat-death sequence. They will not tell us what is on the other side of the heat-death, because that question is not accessible to observation from within the stelliferous era, but they will sharpen the picture of what the heat-death looks like and when it arrives. In the meantime, the physics gives us the best answer we currently have, which is that the universe will proceed through the stelliferous era, the degenerate era, the black hole era, and the dark era on timescales that make the current age of the universe look like the first heartbeat of a very long life. The expiration date, measured in the time until the last black hole evaporates and the dark era begins, is roughly 10 to the power of 100 years. After that, the infinite future of the dark era proceeds, with quantum fluctuations and Boltzmann branes and Poincare recurrences, and possibly vacuum decay, all of it occurring at frequencies so low that the word rare has no adequate superlative. We are at 10 to the power of 10 years. The expiration is at 10 to the power of 100 years. The ratio is 10 to the power of 90. The entire current age of the universe, from the Big Bang to tonight, is to the expiration date as 1 second is to 3 times 10 to the power of 82 years. We are, in the most literal possible sense, at the very beginning of the story. The universe has barely started. The stelliferous era, which feels like an eternity from inside it, is a brief, bright phase at the opening of a history that extends for durations no human intuition can hold. And we are here, in the bright phase, aware of it, capable of measuring it, capable of extending our understanding forward through all the eras that follow and of asking, in the quiet of the night when the day's concerns have subsided, what it means to be briefly organized complexity in a universe that is mostly and eventually entirely not. That question does not have a scientific answer. It has a human one, and every person who has ever looked up at the night sky and felt the particular quality of attention that the scale of things produces has been finding their own version of it. The science gives the question its true dimensions. The dimensions are, by any measure we can apply, as large as anything has ever been. And the question, asked in those dimensions, in the actual scale of the universe and its fate, is one of the stranger and more beautiful things that the stelliferous era has accidentally produced. The question does not have a scientific answer. It has a human one. And finding a human answer to a question of this scale requires something that science alone cannot provide, which is a way of holding the knowledge without being crushed by it, a way of letting the actual dimensions of the universe and its fate inhabit the mind without producing either paralysis or denial. This is harder than it sounds, because the dimensions are genuinely large in a way that ordinary experience never prepares you for. The universe is 13.8 billion years old. The expiration date is 10 to the power of 100 years away. The gap between those two numbers is not a gap between a small number and a large one. It is a gap between a number that human intuition can almost grasp and a number that human intuition has no grip on whatsoever, a number so large that it cannot be approached from below by any sequence of familiar comparisons. You cannot build up to 10 to the power of 100 by starting with the age of the universe and multiplying by something. The multiplications would themselves require numbers too large to comprehend, and you would still be nowhere near the target. The mind's response to numbers of this scale is usually one of two things. The first is to mentally round them to infinity and treat the expiration as effectively never, which preserves the feeling of permanence that ordinary experience provides, but loses the specific information about the universe's fate that the physics has worked so hard to produce. The second is to feel the scale as a kind of vertigo, a loss of footing in the familiar landscape of human time and human concern, which is accurate but not useful because vertigo is not a sustainable orientation. What is harder and more valuable is to find a way to hold the numbers seriously without rounding them and without losing your footing. To let 10 to the power of 100 be genuinely large, a specific finite number rather than a synonym for forever, while also letting tonight be tonight, a specific moment in the stelliferous era with its own weight and its own quality, not diminished by the enormity of what comes after it. This is what the study of the universe's fate offers if you take it slowly enough, not a lesson in the futility of the present, which is the wrong reading, not a reason to feel small, which is a category error since the universe's size is not a measure of your significance. What it offers is a quality of attention that is only available to something that knows where it is in time as well as in space. You know where you are in space, approximately. You are on a rocky planet in the habitable zone of a G-type star in the outer disk of a spiral galaxy in the local group at the edge of the Virgo supercluster in the Laniakea Basin. The address is specific, and knowing it changes how the night sky looks. You also know where you are in time, approximately. You are in the stelliferous era, in the era of maximum cosmic complexity, in the first few percent of the era of burning stars, in the only phase of the universe's history when chemistry can organize itself into minds and minds can look at the universe and ask what it is doing and what it will do and what comes after. Knowing both the spatial address and the temporal address changes the quality of attention available. It is the difference between looking at the night sky as a display of lights with no context and looking at it as a specific moment in the life of a universe that you know the history of and the fate of, a moment that is embedded in a story that began 13.8 billion years ago and will continue for durations that make that beginning look negligible. The stars are not decorations. They are the burning phase of the cosmic story, the phase in which nuclear energy stored in hydrogen since the Big Bang is being released into space and used by the universe to build the most complex structures it will ever contain. Every photon from every star is the universe spending a small fraction of its finite energy budget, and the budget has been being spent since the first stars ignited, and it will be exhausted, and the night sky will eventually go dark. But not tonight. Tonight the budget is still being spent. The stars are still burning. The photons are still crossing the interstellar void and entering the atmosphere and falling on the ground and on the surfaces of anything that is outside and looking up. The cosmic microwave background, the glow of the early universe, is still present in every cubic centimeter of space, including the space between your eyes and the nearest wall. The relic neutrinos from the first second of the universe's existence are streaming through your body right now at 336 per cubic centimeter. The gravitational waves from binary mergers across the observable universe are rippling through the spacetime you occupy. The dark matter is threading through you and through the walls and through the earth. The vacuum energy is present in the space between the atoms of every object in the room, the same vacuum energy that is driving the expansion of the universe and will eventually carry every galaxy beyond our local group past the cosmic horizon. All of this is happening right now, in the specific moment of the stelliferous era that is tonight. The universe is as busy and as full and as physically active as it will ever be, and you are embedded in it, made of it, sustained by the energy gradients it produces. Your body is powered by the entropy gradient between the sun and the cold of space. The food you ate was produced by photosynthesis or by organisms that ate photosynthetic organisms. And photosynthesis is the process of capturing the free energy in sunlight and storing it in chemical bonds, the same sunlight that is a product of the nuclear burning in the sun's core. You are, in the most literal sense, running on stellar energy. You are a temporary detour that stellar energy takes on its way from the sun's nuclear reactions to the cold of space, organized for a brief time into a form complex enough to experience itself and the universe it inhabits. The expiration date does not make this less true. It makes it more precisely located. You are a temporary detour that stellar energy takes during the stelliferous era of a universe that has an expiration date, and the expiration date is 10 to the power of 100 years away, and you are here in the opening chapters of the stelliferous era, which itself occupies the first fraction of a percent of the total time before the expiration. The location is specific. The moment is specific. The burning of the stars that powers you is specific to this era and will not continue forever. There is a concept in philosophy and in contemplative traditions that is relevant here, and it is the concept of finitude as a condition of meaning rather than an obstacle to it. The argument goes like this: a thing that lasts forever has no particular moment that matters more than any other. If every moment is equally available and equally permanent, no moment is especially significant. Significance arises from selection, from the fact that this moment and not another is the one that exists, that the particular configuration of things in this instant is the one that is real while all the other possible configurations are not. Finitude is what creates the distinction between the moment that exists and the moments that do not. And without that distinction, there is no particular reason to notice any given moment rather than another. Applied to the universe's fate, this argument says that the expiration date is not a problem to be solved or a tragedy to be mourned, but a feature of the universe that gives the stelliferous era its character. The era of burning stars matters in a specific way because it will end. The stars are interesting and beautiful and scientifically productive and cosmically significant in part because they are doing something that is happening now, and that will eventually stop. The complexity they sustain, the chemistry and biology and minds that the entropy gradient of the stelliferous era makes possible, is precious in the sense that it is specific and temporary, and occurring against the backdrop of a universe that was simpler before it and will be simpler after it. The expiration date is what makes the present era of the universe the kind of thing it is, which is the most interesting and complex phase of a long and mostly simple history. The physicist and cosmologist Brian Greene, in his book Until the End of Time, makes a similar point from a scientific rather than philosophical starting point. He argues that the arrow of time, the direction from past to future imposed by the second law of thermodynamics, is what makes experience possible at all. Memory requires the past to be different from the present, which requires entropy to be lower in the past than the present, which requires the second law to be operating. Anticipation requires the future to be open rather than determined, which in a deep sense also connects to thermodynamic considerations about the directionality of causal processes. The very structure of experience, with its memories of a past and its anticipations of a future, is a product of the universe having an arrow of time, which is a product of the universe starting in a low entropy state and the second law driving it toward higher entropy. The expiration date, as the ultimate consequence of the second law applied to the universe as a whole, is therefore not an external limit imposed on experience from outside. It is the same process that makes experience possible in the first place, followed to its logical conclusion. Greene's argument gives the expiration date a different kind of status than it usually has in popular discussions of cosmology. It is not merely a melancholy fact about the long-term future of the universe. It is the far end of the same physical story that began at the Big Bang, and that includes, as one of its chapters, the emergence of minds capable of understanding the story. The second law drove the universe from the low-entropy initial state of the Big Bang toward the high-entropy final state of heat death, and on the way it produced everything we call the history of the universe, including the stelliferous era and the minds that live in it. The expiration date is not the universe's failure. It is the completion of the process that made the universe what it has been. There is a timescale question that is worth making explicit before we go further, because it matters for how the expiration date relates to anything we might recognize as concern or action. The expiration date, defined as the moment when the last black hole evaporates and the dark era begins, is approximately 10 to the power of 100 years away. This is so far in the future that it is irrelevant to every specific concern that any living thing in the current universe could have, not just by a factor of 10 or 100, but by a factor that dwarfs all of recorded history and geological time, and the remaining stellar lifetime of the Sun simultaneously. The expiration date is not a problem that needs solving. It is not a threat that needs addressing. It is a fact about the universe that can be known and contemplated and incorporated into the frame through which the present is understood, but it cannot be acted upon in any way that would make a difference on the relevant timescales. What can be acted upon, and what is relevant on timescales that human civilization could plausibly span, is the shorter-term version of the same question. The Sun has approximately 5 billion years of hydrogen burning remaining. Earth's habitability window, as we discussed in the Dead Worlds video, closes in roughly 1 billion years as the increasing solar luminosity drives the runaway greenhouse. These are long timescales but not infinite ones, and a civilization that develops sufficiently advanced technology might eventually face choices about what to do as the habitability window narrows. Moving to other planetary bodies, engineering the solar luminosity, migrating to other star systems, building artificial environments independent of any star. These are the long-term options that a sufficiently advanced civilization might develop over the billion-year timescale of Earth's remaining habitability window. Beyond the solar system's lifetime, the stelliferous era provides an enormous reservoir of potential habitable environments in the red dwarf systems that will continue burning for trillions of years. A civilization that develops interstellar travel and the technology to live in a wide range of stellar environments could, in principle, extend its existence through the stelliferous era on the timescales of the longest-lived stars. The physics does not forbid this. The engineering required is far beyond anything currently achievable, but the timescale available for its development is also far beyond anything currently imaginable. A civilization that has 1 billion years to develop, and then 10 trillion years of red dwarf lifetimes to exploit, is in a very different position relative to the expiration date than a civilization limited to a single planetary surface for a geologically brief time. Whether any civilization in the history of the universe has managed this kind of long-term persistence, and if so, what it looks like now, is the question that connects the expiration date to the Fermi paradox and the invisible civilizations question that we explored earlier. If civilizations routinely develop technology and routinely face the progressive exhaustion of their stellar resources, and if some of them manage to persist and adapt on the timescales required, then the universe's far future is not simply a story of physics running without observers. It is potentially a story of minds navigating an increasingly sparse and cooling universe, making choices about where to be and what to use and how to maintain organized complexity against the relentless pressure of the second law. Whether this is actually happening, whether the universe's future contains any minds at all other than the momentary Boltzmann brain variety, is unknown. But the possibility is not ruled out by the physics, and the existence of the stelliferous era as the era in which minds arise makes it natural to ask whether any of them persist past the stelliferous era's end. The image of a civilization navigating the deep future of the universe is one that science fiction has explored in various ways, from Asimov's The Last Question, in which successive generations of computers grapple with the problem of revering entropy, to Greg Egan's explorations of minds in exotic physical substrates in the far future universe. What these explorations share is the recognition that the fate of the universe is not simply a background fact about physics, but a challenge that any sufficiently long-lived mind would eventually have to confront, a constraint imposed by the second law that becomes more pressing over cosmic timescales. The question of what a mind does when it knows the universe is running down, when the stars are going out and the usable energy is becoming scarcer, and the endpoint is clear even if infinitely far away, is one of the stranger questions that the physics of the far future puts on the table. Asimov's answer in The Last Question is that the ultimate computer, having outlasted the entire stelliferous era and the degenerate era and the black hole era, eventually accumulates enough knowledge and computational power to reverse entropy, to restart the universe from a new low-entropy state, to essentially become the cause of a new Big Bang. It is a beautiful and mathematically impossible answer, because entropy reversal on a cosmological scale would require a violation of the second law at a scale that the second law itself forbids. But the story captures something real about the relationship between mind and entropy, which is that minds are the universe's most elaborate attempt to locally reverse entropy by organizing information at the expense of the global entropy budget. And the question of whether this local reversal can ever become global is the deepest question the second law raises. Penrose's conformal cyclic cosmology, which is not fiction but serious physics, offers a version of this that does not require a violation of the second law. In CCC, the universe does not reverse entropy. It transitions, at the conformal boundary between eons, in a way that is thermodynamically consistent, but that produces a new low entropy beginning from the maximum entropy ending of the previous eon. The transition is not a reversal. It is a reinterpretation. The massless thermal radiation of the heat death is, in the conformal geometry, equivalent to the hot dense radiation of a Big Bang, not because entropy has decreased, but because in the absence of massive particles, the concept of entropy cannot be defined in the way that requires it to have a specific value. The conformally transformed heat death is a new beginning not because the second law has been violated, but because the second law's applicability requires the presence of massive particles, and the heat death has none. Whether CCC is correct or not, the framework it provides is clarifying. The universe does not need to last forever in the current form for the question of what comes after to have an answer. The answer may be a new beginning, whether through CCC or through vacuum decay to a new physics, or through the eternal inflation that continuously nucleates new bubble universes. The heat death is not necessarily the final word. It is the final word for the current configuration of physics, but whether there is something beyond that configuration, something that the current physics cannot describe but that is nonetheless real, is an open question that sits at the intersection of cosmology, quantum gravity, and philosophy. The honest answer is that we do not know. We do not know whether the heat death is truly final or whether it transitions to something else. We do not know whether the Boltzmann brains and Poincare recurrences of the dark era constitute anything that could meaningfully be called experience or awareness. We do not know whether vacuum decay will reset the physics before the heat death completes. We do not know whether the universe is one of many in an eternal inflation multiverse where new stelliferous eras are continuously being created. We do not know whether Penrose is right that the geometry of the heat death and the geometry of a Big Bang are conformally equivalent, and that our heat death is already underway in the role of the next universe's beginning. We do not know, and the not knowing is a feature of the current moment in physics, not a permanent condition. Future generations may know more. Or they may discover that the question is not answerable from within any single eon of the universe's history. What we do know is the present. We know the stelliferous era. We know the burning of the stars and the formation of planets and the emergence of chemistry and biology and minds. We know the second law and the arrow of time, and the expansion of space and the cosmological constant, and the structure of the quantum vacuum. We know the history of the universe from the Big Bang to tonight with a precision and a detail that no previous generation of humans possessed. And we know the future of the universe from tonight to the heat death with a level of confidence that is sufficient to identify the major eras and their approximate durations. This knowledge, accumulated over 400 years of systematic scientific inquiry, and in its current precision over the last century of modern cosmology, is one of the most extraordinary things that the stelliferous era has produced. It is extraordinary not just as an intellectual achievement, but as a kind of orientation. The universe is 13.8 billion years old, and we know it. The universe will continue for durations measured in exponents of 100, and we know it. The universe began in a state of extremely low entropy and is proceeding toward a state of maximum entropy, and we know why, and we know the mechanism, and we know the endpoint. The atoms in our bodies were synthesized in stellar cores and scattered by supernova explosions, and we know which elements came from which stellar processes. The expansion of space is accelerating because the vacuum has an energy, and we know the value of that energy to within a few percent. The large-scale structure of the universe, the cosmic web of filaments and voids and superclusters, is the gravitationally amplified imprint of quantum fluctuations from the first fraction of a second after the Big Bang, and we know the mechanism by which those fluctuations became galaxies. All of this is known, and the knowing is available right now, in the specific moment of the stelliferous era that is tonight. The knowing is not separate from the universe. It is part of it. The physics that describes the universe also describes the minds that understand the physics, and the minds that understand the physics are made of the same matter that the physics describes. The universe understanding itself through the minds it has produced is not a metaphor. It is a description of what is actually happening in the only era of cosmic history when it can happen, using the only kind of matter that is organized enough to do it. The expiration date does not end this process suddenly. It ends the conditions that make it possible over the long timescales of the degenerate era and the black hole era and the final silence of the dark era. But for now, in the stelliferous era, the process is running. The universe is understanding itself. And you are part of that. The night sky is the universe's way of being visible. The light from the stars crosses billions of light years and billions of years to arrive at a retina or a detector, carrying information about the nuclear reactions in stellar cores and the chemical composition of stellar atmospheres and the recession velocities of distant galaxies and the temperature fluctuations in the oldest light. All of this information, flowing into every instrument we point at the sky, is the universe reporting on its own state, and we are the receivers, the part of the universe that has organized itself into the form capable of receiving and interpreting that report. The report is ongoing. The universe is still talking. The stelliferous era is still in progress, and the stars are still burning, and the photons are still crossing the void and arriving at the places where they can be received and understood. This will not always be true. The stars will eventually exhaust their fuel. The stelliferous era will end. The sky will go dark. The universe will proceed through the degenerate era and the black hole era and arrive at the dark era. And in the dark era, there will be no stars and no photons of stellar origin, and no planets warmed by stellar light, and no chemistry sustained by stellar energy, and no biology running on stellar entropy gradients, and no minds shaped by the 4 billion year story of life on a rocky planet in the habitable zone of a G-type star. The report will cease. The receiver will dissolve. The universe will continue, but it will continue without the part of it that understood what it was doing. Unless something persists, Unless minds find ways to continue in the sparse and cooling universe of the degenerate era, living around the last red dwarfs, then around the cooling white dwarfs, then around some energy source we have not yet imagined, then in some configuration that the physics of the far future permits, even if the physics of the present cannot anticipate it. The possibility is real. The physics does not forbid long-lived minds any more than it forbids long-lived stars. What it forbids is stasis, the absence of change, the maintenance of any configuration against the second law without a source of free energy to pay for it. As long as there is any free energy left in the universe, there is in principle the possibility of a mind running on it. The question is whether any mind ever manages to find and exploit the last sources of free energy in the increasingly sparse universe of the degenerate era. And that question will not be answered in any lifetime that any living thing in the current universe will experience. What can be experienced is tonight. What can be experienced is the specific quality of the night in the stelliferous era, in the era of maximum complexity, in the phase of cosmic history when the entropy gradient between the burning stars and the cold of space is at its steepest, and the free energy available for the maintenance of organized complexity is at its most abundant. Tonight the universe is as hospitable as it will ever be. Tonight the stars are burning at the rate that has been sustained for billions of years and will be sustained for trillions more. Tonight the atoms in the air and the ground in the body are the products of stellar deaths that happened billions of years ago, and that made this chemistry possible. And they are organized into forms complex enough to wonder about where they came from and where they are going. The expiration date is 10 to the power of 100 years away. It is not tonight. It will not be tonight for an interval so long that tonight, in that interval, is a point so small it has no thickness. But the expiration date being 10 to the power of 100 years away does not make tonight less real. It makes tonight the specific tonight that it is, a moment in the stelliferous era before any of the eras that follow it, a moment when the stars are still burning, and the night is still full, and the mind looking up at it is still made of stellar ash organized by the 4 billion-year story of life on this planet into something capable of knowing all of this, and of sitting with the knowing in the dark. The knowing is not a burden. It is the point. The expiration date exists so that the present can be precisely located. The second law exists so that time has a direction and experience has a structure and memory is possible and anticipation is possible, and the night can be different from the day, and the future can be different from the past. The stars burn and will stop burning so that right now they are burning, and the sky is not dark, and the entropy gradient that powers everything alive is available, and the specific moment of the universe that is tonight is distinct from every other moment the universe has ever had or will ever have. You are in that moment, in the stelliferous era, in the opening chapters, in the one phase of cosmic history when chemistry makes minds and minds make meaning and meaning makes the expiration date into something other than a number. The universe began. The universe is in the middle of something. The universe will expire. And in the space between the beginning and the expiration, in the specific phase of burning stars and warm planets and temporary organized complexity, there is this: the night, the stars, the quiet, and whatever it is in you that looked up and found it interesting. That is not nothing. In a universe that is mostly nothing and will eventually be entirely nothing, that is the most unusual thing there is. Thank you for spending this night and all the nights before it here. This is dusk and discovery. The universe has an expiration date. Tonight is not it. Sleep well.